Hello and welcome to the CSE Senior Design Group 12 final presentation on the Automated Black Bear Detection and Deterrence System. This project was done in collaboration with ECE Group 2621. A little background on our project. Our sponsor is Interface Technology, who wants to address the rising number of conflicts and home entries by bears within the state of Connecticut. The goal is to create a device to deter bears away from people's homes by using overwhelming stimuli. Last year's group was able to create a functioning prototype, but when tested in the field, the stimulus was not enough to deter the bear. Our goal this year was to improve the deterrence capabilities as well as the speed and reliability of the device. The device itself consists of a Raspberry Pi that is running the You Only Look Once computer vision model that will identify when a bear walks into the camera's frame. This will trigger the stimuli that includes loud sound and bright light. Last year's project consisted of a Raspberry Pi 4 running the YOLO V8 Nano model with a generic USB camera, a 100 decibel speaker, 6,000 lumen light, as well as a front-end UI. This year, we upgraded to a Raspberry Pi 5 running the NCNN compiled version of the YOLO V11 Nano model, a 120 decibel air horn with an automatic air compressor, and a 12,000 lumen light with the same generic USB camera.
Another part of this project that we worked to improve was the testing and optimization of the YOLO model. So the YOLO model is a computer vision model that can take in one image, in this case one frame of our video stream, and detect a variety of animals and objects that are pre-trained on the model. So we developed a variety of programs to benchmark all the different releases of this model as it's open source, and we measured a bunch of the metrics of how the model was performing on our device. And we also created a sample data set to simulate a real video feed to ultimately determine the best option. So here's an image of the baseline test on the Pi, and with some comparison of this information, we decided we wanted to use the YOLO 11 Nano or N model, as it had some of the best metrics and also some of the highest accuracy out of all the models, while also being the newest and having some of the best feature updates as well. And going into testing the model optimizations, we tested a variety of strategies such as quantization, motion detection, frame skipping, and resolution downscaling, with the goal of finding the most relevant optimizations for our hardware. As with the previous year's project, there was actually a 7-second delay between the detection of the bear and the triggering of the deterrence, as the model was taking up a lot of the computation and being very slow and just slowing down the whole operation. So this testing provided us with a clear view of the improvements of the model. And the first one that we looked at was the usage of quantization, which is converting high precision numbers used in calculations to lower precision formats. And while this exact change did not give us much optimization, there is a separate format of the YOLO model called an NCNN format, which is optimized specifically for mobile processors, which the Pi has. And upon using this, we were able to drastically increase the frames per second and lower the latency, which is exactly the achievement we were trying to implement. And another optimization that we added was motion detection, where we would take 2 frames and compare the amount of pixels that changed between those frames. And if the number of pixels was above a certain threshold, it would then run the model. And this would save a lot of computational power because it would only run the model when motion was detected, meaning that it wouldn't be running it the other 99% of the time. Another optimization technique we tested was frame skipping, which allows us to, instead of running the model every single frame that's available, we'll run it every few frames. And since the model is taxing, that also saves a lot of computational power from the CPU. And these images on the right show that with a frame skip of 0 versus a frame skip of 10, we save about 40% of CPU usage. And the last optimization technique that we tried out was resolution downscaling, which would be lowering the resolution of the input image to the model. And this increases the performance of the model by decreasing the number of pixels that need to be processed in the model. And the chart at the bottom also shows that the lower we went with the resolution, the higher the FPS went, and also the savings in CPU usage. And as for the final model adjustments and the final optimizations we used, we tested various combinations of these optimization strategies to find the best combination possible. And we found that when combining frame skipping and motion detection, they were conflicting, because when the motion detection was triggered, sometimes the frame it was triggered on would not be a frame that the model would trigger on for frame skipping. So we decided to remove frame skipping, as the total number of saved frames where the model is running was much higher with motion detection than frame skipping. So the ultimate optimization suite that we used was the NCNN format with motion detection to limit how much the model is running, as well as the resolution downscaling to lower the number of calculations needed for the model.
For our main detection loop, it first waits for motion to be detected. When that happens, it will check that if any of the objects in the frame are identified as an animal. From there, if it has been more than 30 seconds since the last detection has occurred, then it will log the detection and save the image both on the Pi and push it to the front-end UI. From there, if it is detected as being a bear, it will trigger the horn and light.
For the backend redesign, we detected multiple bottlenecks, their architecture, tightly coupled detection, logging, and web services, which could potentially introduce high latency. Furthermore, the old system relied on the front end constantly pulling the server, which was inefficient and slowed down response times. We decided that a decoupled stateless relay model where the Raspberry Pi functions as a dedicated edge sensor was the best approach for improving latency. For the synchronous pipeline, we decided to separate the primary YOLO detection and deterrent triggers from non-essential network operations. We did this by implementing 2 threads, the upload thread and telemetry thread, to handle data transfers without blocking the main detection loop. For real-time communication, we decided to integrate WebSockets. This replaced the polling that the last year's group implemented, and instead we used Flask socket IOs to enable instant bidirectional updates between the server and the dashboard. Furthermore, this allowed for automated updates. We used broadcasts to allow for pushing images and telemetry data almost instantly to the UI upon detection or upon a set interval. And lastly, latency. Moving to a push model reduced perceived user latency from seconds to milliseconds. For the command and control, we decided to leverage server-sent events via the following API endpoint, as we see on the slide for persistent control channels. The Pi maintains an outbound connection, allowing for remote overrides without requiring complex port forwarding. User actions on the dashboards are queued and delivered to the Pi in real time for instant hardware activation. And lastly, for system health and telemetry, so for edge monitoring, it collects high-resolution metrics on CPU usage, thermal data, and memory stats using the PSUtil library. A background thread posts health data every 30 seconds to the server to avoid interrupting the main detection loop. And these health metrics are relayed to the dashboard, providing live visibility into the device's performance and stability.
On the front end, we had to redesign the last year's project because of several limitations that it had. It relied on a multi-page login-style architecture with authorization requirements everywhere that felt disconnected and clunky. Furthermore, the biggest bottleneck was the polling-based communication system that sends messages at regular intervals and causes a constant lag time to appear in the Pi. This is inefficient, so we decided to scrap all the files in the front end and redesign it completely, such as the ones you can see on the screen with the .back and .old that are all redundant and useless. We decided to move forward with a modern stack using Vite, React, and TypeScript, where you can see several different features on a single page. This is a redesigned Bear Begone dashboard. Our goal was to have a single page that could show you everything about the results of the project according to the Figma design that we made beforehand. On the left, we have real-time telemetry data with the CPU temperature, usage, memory, disk usage, and uptime. On the center, we have the last detection feed that shows the latest threat detected in the camera that sends to the Pi, to the backend, and all the way here to the front end. On the right is our event log where you can view past detections if you missed past views. The programming behind this is our WebSocket system via socket.io. Unlike the old polling method, the backend now pushes detections to the front end the millisecond that they happen. We also implemented features such as a cache busting strategy, where you can see in the code snippet that we append a timestamp to the image URLs, forcing the browser to display the latest bear capture rather than showing a stale cached image. We also used a seamless event log where incidents populate automatically without a page refresh, and you can view any past incidents that occur without any delay. Finally, we conducted full stack simulation testing where we used everything except for the hardware that brought the stimuli. Since we couldn't bring a 500-pound black bear into the lab, we had to use high-res printouts to trigger the YOLO version 11 model running on the Pi, as you can see in the photos. The Pi was connected to the MacBook and other computer that we used to run the backend and front end, which allowed us to debug the WebSocket disconnections and payload timing in a controlled environment. The results of this were that the dashboard reliably updates with new values and images automatically that the millisecond we detect a bear occurs, and we've confirmed that the software logic is rock solid and ready for the final hardware integration.
For our field testing of the device, we were able to take it to our sponsor's backyard and set it up alongside 2 game cameras that would be able to capture images and video of the interaction between the bear and the device. We also had access to a Wise camera that would give us a live feed of our testing site. And you can see here, there are 2 towels hanging from the tree that are saturated with a bear attractant to attempt to lure in the bear. And now here's a clip from when a bear approached the device during live testing. As seen in the clip, the stimuli that we chose this year was successfully able to scare away a bear once it was triggered. This, alongside the improved performance in the Pi running through model optimization, as well as a streamlined front end for users to review when the device was triggered, shows that this is a viable way for us to detect and deter bears. Thank you for taking the time to watch this presentation.